Hello, so for this video we are going to go over the Ionic Bonding's Gizmo, and let's go ahead and get started. We will be completing the majority of this document, so follow through. So in this first section we're over here looking at this example of Nate and Clara and how they have markers. So there are 8 markers in a set, Nate has 9 markers and Clara has 7 markers. So just to be clear, they each need 8 markers. So in this situation, what they need to do is pretty much exchange markers. So this has to do exactly with ionic bonding as opposed to covalent bonding. In ionic bonding, we exchange electrons where one element will lose electrons while the other one will gain electrons. And typically the metal atom will lose electrons and the non-metal atom will receive electrons. So let's explore this. So down here we start off with this model where we compare sodium and chlorine, and overall we're just looking at this gizmo. Notice we have sodium and chlorine. We can show the formula of our eventual molecule that we will make. Let's just click check here. Let's hide the inner electrons. We don't really care about these because once again we are only dealing with valence electrons. So in each case we want to either gain or lose electrons to complete our octet and to fill up our valence shell to stabilize these atoms. So what we're going to do here, we can always drag and drop electrons. I'm going to go ahead and reset this, but I can never drag and drop from the nonmetals because the nonmetals, notice the nonmetals cannot lose electrons, they only gain electrons in our situation. So there it is, and we go ahead and check, and we have completed and stabilized our elements. Notice that sodium has a complete valence shell of 8 electrons, while chlorine has another complete valence shell of 8 electrons. We'll be showing the charge. We'll be making sense of this later. So overall, we already completed the section. And notice what happened. We stabilized our atoms, but we also ended up with a charge. Okay, so let's go down here. So in this situation, we're just asked to label the number of electrons, the total number of electrons for each atom. For sodium, for instance, we have initially, so we're going to reset this, and we're going to go ahead and show our inner electrons. You notice we have 1, 2, 4, 6, 8, 10, and 11 electrons on sodium. Chlorine, on the other hand, has 2, 1, 2, 4, 6, 8, 10, 12, 14, 16, 17 electrons. Now in our previous unit we did discuss that for protons and electrons, if we have a neutral atom where it is not charged, the protons equal the number of electrons, so sodium has 11 and chlorine has 17. In this situation here, most atoms are stable with a configuration of 8 electrons. This is known as the Octet Rule. And now we're trying to understand how many valence electrons each atom has. So let's go ahead and hide our inner electrons. And notice we have 1 valence electron for sodium and 7 for chlorine. Let's go ahead and fill that out. Now in this situation, we previously moved our outer electron from sodium and dropped it in chlorine. We checked our element and we stabilized our elements. So notice we ended up with a positive one and a negative one. This is pretty much showing the ratio of protons to electrons. So at this moment, we have 1 more proton than electrons because we had lost an electron. So now we are more positive. Over here, we lost, my apologies, we gained an electron. So now this element is more negative. And if you notice, the sodium atom got smaller, and chlorine looks like it stayed the same, but it actually got slightly larger. So we're going to show that is now positive 1, and chlorine is negative 1. And is each ion stable? Yes, it is stable. So we check it, and once again, it is stable because we completed the Octet Rule. So the valence shell is now complete. So go ahead and fill it in. And try to answer this question down here and check with the teacher to answer this, or to get the correct answer. Now for part B. In this situation, we are going to be stabilizing all of these combinations down here and writing out the chemical formulas. So I'm going to go ahead and do lithium and oxygen, which is forming lithium oxide. So let's go ahead and click on lithium. And oxygen, we're going to show all the electrons. And lithium is a small element, so it's only going to be stabilized with 2 electrons, whereas oxygen will be stabilized with 8. So let's go ahead and see what happens. So we're going to go ahead and answer all these questions. You make your assumption about how much lithium has to lose to be stable, and how much oxygen needs to gain to be stable. So notice right here, look closely, remember, you need a full valence shell. And in this case, it would be easier to lose an electron for lithium to have a valence shell, and it'll be easier for oxygen to just gain an electron. But let's check for the stability. These elements are not stable. Lithium is stable, it has a full valence shell. However, oxygen is still missing 1 element here. My apologies, 1 electron. It is missing 1 electron here. So I'm going to go ahead and add a metal because we need to donate to it. So let's go ahead and donate and check. And now it is stable. We have now completed lithium oxide. So what does this look like? Did we stabilize the compound? Oh yes, we did. And down here we're going to write out a formula. So we're going to go and write out lithium, control comma to write that little 2, control comma to go back to O, and there's lithium oxide. What was the charge for each ion? We had a positive 1 here, positive 1 for this lithium, and oxygen ended up being turned into an oxide with a charge of -2 because it accepted 2 electrons, whereas lithium lost an electron. So once again, we have the formula right here. Now we scroll down a little bit. I will help you out with lithium fluoride. And I'm going to reset this. Now we're going to go with fluorine. And notice we are stuck in a situation with the same element here, lithium and fluorine. So fluorine will have a valence shell that has 7 electrons. So it has 7 valence electrons, whereas lithium still has 1. So we go ahead and donate. We check it, and we're good. It has a complete valence shell of 8 electrons. So all we do here is write out the charge on this lithium and the charge on fluorine, which is -1. As far as the formula goes, we just write lithium fluoride. Anyways, go ahead and complete these other items right here. Check with your teacher to see if your answers are correct. Be careful with this one. This one will be a little bit tricky. Think about it as a teeter-totter. And same thing with aluminum chlorine. It'll be a bit more demanding. So for this extended version right here, we are looking at lithium only. So let's go ahead and clear out fluorine. Reset. I'm going to drag and drop fluorine into the trash. And now we only have lithium. So notice we are being told to analyze lithium. And then we're asked to compare, to check lithium on the periodic table and to see if there's any other element from this column here, from this same group, alright, from group 1 that is present in the gizmos. So we go back and check our metals, and we notice that sodium is the other element that is present there. So if we go ahead and focus on lithium, for instance, we see that it has a valence, 1 valence electron, and then sodium also has 1 valence electron here. Alright, 2 in the first ring, 8 in the second ring, and in the third ring, it is only 1 electron present. So now we go back, and we go ahead and fill this out. So you're pretty much going to be checking that out and comparing the valence electrons for all of these items here. Refer back to periodic table and to this chart right here, and go ahead and fill out this chart. Check with your teacher to see if you are correct with your answers. Just a reminder, click on these elements. For instance, boron has 3 valence electrons, carbon has 4, and fluorine, notice it has a 7 right here.